the Groningen gas field, the natural gas produced is freed from undesirable constituents such as sand and liquids. After this, the gas is dried. The drying is necessary to avoid condensation of the heavier hydrocarbons during transport through the pipeline network. In the drying process, use is made of the cooling which occurs when the gas expands from wellhead pressure, here about 200 bar to 74 bar. Despite the drying, it's apparently still possible for a certain amount of condensation to take place in the transport pipelines. The reason for this is the physical behavior of the gas. The hydrocarbon dew point exhibits retrograde condensation. The dew point rises at decreasing gas pressure. Here we have the curve of the hydrocarbon dew point of Groningen natural gas, with the gas pressure plotted on the horizontal axis and the temperature on the vertical axis. During the field drying process, the temperature of the gas drops to minus 12 degrees centigrade. The gas pressure is then 74 bar. Despite this, condensation can still occur at locations in the pipeline network where the prevailing pressure is between 20 and 40 bar, namely when the ground temperature drops in winter. Gasunie have undertaken an extensive investigation with a view to ascertaining at what points in the transport system condensate is likely to form. This is the beginning of the pipeline network. The dried gas comes in at a pressure of 66 bar. Via the mainline network, the gas is transported all over the Netherlands and to the frontiers. Pressures in this network range from 66 to 45 bar. At over 50 points, the measuring and regulating stations, the pressure is reduced to 40 bar to supply the regional network. Gasunie take advantage of the pressure drop at the measuring and regulating stations to subject the gas to a second drying process. Little or no heating is applied to the gas prior to its expansion at the station. The expansion causes the temperature of the gas to drop, in winter often to 0 degrees centigrade or even lower. The temperature drop gives rise to the formation of condensate mist. Measurements are performed to establish at what distance after the station the mist has precipitated in the pipeline. A probe is introduced into the transport pipeline and enables a slight volume of gas to flow to the measuring instruments. Such measurements have been carried out at increasing distances from the station, up to the point where the gas no longer contained any mist. The investigation has shown that the distance over which the mist precipitates downstream of the station ranges from 200 to 500 meters, depending on the pipeline diameter and the gas velocity. A liquid receiver installed in the pipeline at that point enables all the condensate formed to be collected. What happens downstream of the station can be seen from the course of the condensation curve. Expansion to 40 bar causes the gas temperature to drop. This in turn gives rise to condensate in the form of a mist. When the condensate is separated from the gas stream, the dew point drops to far below the ground temperature at pipeline depth. This drying by expansion at the measuring and regulating stations is so effective that hardly any further condensate is likely to be formed further down the network. At low gas velocity, the condensate flows like a brook along the bottom of the pipe. This is stratified flow. When the gas velocity increases, wave flow occurs. At even higher gas velocities, the liquid begins to atomize. Ultimately, annular flow develops when the liquid flows as a film along the whole of the inner wall of the pipe. In 40 bar lines, this annular flow occurs at gas velocities in excess of 5 meters per second. In a lot of places, the gas pipelines dive under rivers and canals. At low gas velocity, liquid can accumulate in these crossings. In autumn, when the gas offtake rises, the gas velocities increase, creating conditions likely to give rise to liquid being blown out of these crossings in slugs. At gas velocities in excess of about 4 meters per second, the condensate flows through the crossing without any difficulty. Liquid is also likely to accumulate upstream of dike crossings and can then be carried along by the gas when its velocity increases. The regional network, which branches out at numerous points, starts at the measuring and regulating stations. How does a flow of condensate behave at a branch point? This is the model of a pipeline with a branch line. The gas stream comes from the left. The gas flow in the branch line is measured with the meter on the left. The meter on the right measures the gas flow in the straight-through line. At this moment, the gas stream divides into two equal parts. It now appears that all of the liquid passes into the branch line. Next, we lower the gas flow entering the branch line to 30%. All of the liquid still continues to flow into the branch line. It's not until a small part of the gas stream passes into the branch line that liquid flows straight through. In most cases, the liquid flow does not divide at a branch point, but either goes straight on or into the branch. Hence, the liquid flow shows a distinct route preference. In this particular model, the branch line is of smaller diameter than the straight line. If the gas stream divides into two equal parts, the liquid flow will in this case also take the branch line. When the gas stream through the branch line is reduced, all the liquid will at a given moment go straight on. Route preference also occurs with complete annular flow. In view of the route preference mentioned, it follows that any condensate formed at the beginning of a regional pipeline network will generally flow to a single terminal branch of this network. It's possible to calculate to what offtake points the condensate is likely to be carried, where appropriate measures can then be taken. A special case of route preference occurs with large double underwater crossings. Each leg of the crossing carries 50% of the gas stream. Route preference causes the liquid to flow to the reserve leg, where it accumulates. By closing off the straight-through leg, the gas velocity in the parallel leg is doubled, thus causing the liquid present there to start moving. This is the pipeline situation at the inlet side of a gas delivery station. The gas comes from the left and divides over the meter runs. It appears that the liquid carried along accumulates at the last meter run. The liquid separator in this particular meter run is already half filled, while the liquid traps in the other two runs are still practically empty. The separator in this meter run must therefore be designed to handle all the liquid. A simple device to catch liquid in gas pipelines is the siphon trap, an opening in the bottom of the pipeline in which the condensate collects. The siphon trap functions effectively as long as the liquid flows along the bottom of the pipe. As soon as annular flow occurs, the catching efficiency rapidly deteriorates. A siphon trap installed at a short distance downstream of a bend does not function properly. Having passed through the bend, the gas flow is highly turbulent, and consequently, the liquid at that point does not flow along the bottom of the pipe. For this reason, a siphon trap must be installed at some distance from the bend, at a point where the gas flow has calmed down again. A siphon trap installed in a dead-end line does not function at all, as can be explained from the route preference of the liquid. In this setup, the siphon trap is also located in a dead-end part of the line. This time, however, the branch line ascends at a slant. The siphon trap is now capable of catching liquid, provided the gas velocity is low. As soon as the gas velocity increases, the liquid flow will once more prefer the rising branch line instead of the straight-through line to the trap. The Gasunie laboratory has tested the catching efficiency of a pipeline siphon trap as a function of the gas velocity under practical operating conditions. These measurements reveal that in 40-bar lines, the efficiency of a siphon trap is adequate as long as the gas velocity remains below 5 meters per second. At gas velocities in excess of 5 meters per second, the efficiency drops off rapidly. To remove condensate also at high velocities, Gasunie have developed a liquid separator of their own. Its operation is based on locally lowering the gas velocity, causing the annular flow in the line in the widened part to be converted into flow along the bottom of the pipe. The widened line portion must be so long that the gas stream entering at high velocity will have steadied down by the time it comes to the point where the liquid is separated from the gas stream. The liquid receiver is also suitable for catching slugs. The blow-by is only slight. After a series of practical tests, 200 liquid receivers of this type were built into the regional pipelines downstream of all the measuring and regulating stations. Gas delivery stations are protected against condensate trouble by a liquid trap downstream of the measuring and regulating station and by a separator upstream of the delivery station. With a view to attaining absolute protection, laboratory tests have been carried out using models to ascertain whether any condensate that has managed to slip through can be caught in the dust filters installed at the beginning of the meter runs. Condensate was found to collect in the dust filter pot at low gas velocities. At higher gas velocities, however, the liquid inside the dust filter pot behaves so wildly that it's forced out again right away. Here you see the performance of the dust filter at the same velocity as before, but this time a vessel has been connected to the drain opening. This has reduced the blow-by considerably. Clearly, therefore, a dust filter equipped with a vessel can serve as a liquid receiver. Separators are installed at the inlet side of measuring and regulating stations to protect the station against inconvenience from condensate. An arrangement at a measuring and regulating station is used to test the liquid catching efficiencies of the different types of separators under practical conditions. The gas stream passing through the station can be wholly or partly conducted through the testing installation. During a given period of time, liquid is injected into the gas stream flowing towards the separator. The blow-by of the separator is collected and measured. Apart from measuring, the efficiency efforts are also made to improve the performance. In the laboratory, the operation of standard separators is simulated with the aid of a model. A pitot tube is used to measure the gas velocities in the cyclone space. The operation is then studied visually. These investigations reveal whether the performance can be improved. The liquid separation is then once more examined in respect of the modified model. Modifications which have proved valuable in the model are examined under practical operating conditions. Here also, the flow behavior is measured with a pitot tube. The investigation has provided insight into the formation and the behavior of condensate in gas transport systems, and thus into the ways and means whereby inconvenience can be avoided. The chance of vital installations